Okay, so in this part of the lecture, we are going to do a review on the Bode plots. So let us assume a simple transfer function t of s equals to 1 over 1 plus s over omega 0. And we would like to draw the asymptotic Bode plots, the asymptotic magnitude Bode plot, and asymptotic phase Bode plot. We know that the magnitude of t is equal to 1 over the square root of 1 plus omega over omega 0 all squared. And the magnitude in GB for t is 20 log magnitude of t, which is equal to 20 log 1 minus 20 log the square root of 1 plus omega over omega 0 squared for this example. 20 log 1 tends to 0, and therefore the magnitude in dB for t is minus 20 log the square root of 1 plus omega over omega 0 all squared. And in order to be able to draw the magnitude plot in dB, we need to identify at each frequency point what is the value of this magnitude. What we know and what we really often refer to is the true value of this magnitude in dB at omega equal omega 0, because if we want to set omega equal to omega 0, this value here becomes minus 20 log of the square root of 1 plus omega equal to omega 0 over omega 0 per squared. So this is minus 20 log the square root of 2, which is equal to minus 3 dB. Therefore, we know that at omega 0, the magnitude will be minus 3 dB, and this is the cutoff frequency, or the 3 dB frequency of the transfer function. Of course, for very small omega, at very small omega, right, at omega close to 0, we have, at very small omega close to 0, we have the magnitude of t is equal to 1, and therefore 20 log magnitude of t is equal to 0 dB. Then it starts at 0 dB and it drops to minus 3 dB at omega equal to omega 0. Okay, we want to draw the asymptotic plot, so we are going to split the region into two regions around omega 0. The region where omega is smaller than omega 0 is the first one. Okay, and for this we need to approximate the function. So if omega is much smaller than omega 0 asymptotically, then omega over omega 0 squared is much smaller than 1. And therefore we can drop this, and therefore we can assume that the 20 log magnitude of t becomes 20 log 1, which is around 0. Therefore the asymptotes, okay, when omega is much smaller than omega 0, this amplitude tends to 0. So we tend to represent the Bode plot, magnitude Bode plot, by a straight line with a constant level equal to 0 dB before omega 0. The second region that we are interested in is the region where omega is much greater than omega 0, and we would like to draw the asymptote there. Now, if omega is much greater than omega 0, this means that omega over omega 0 squared is much greater than 1. Okay, this means that I can ignore the 1 here. Now with the square root and this of a squared term, we wind up with the magnitude in dB being equal to minus 20 log omega over omega 0. Okay, now this is the approximation for the transfer function magnitude in this region. Now we are going to see how we draw the asymptotic Bode plot. To do this, we know that as you have learned before, that here we draw a line with a slope equal to minus 20 dB per decade, because here I have a pole, and we will learn the rules for that, but let us just take refresh where this came from. Okay, so let me consider 2 points. The first point is point 1, okay, And so 0.1 is here, and at 0.1, omega over omega 0 is equal to x. So the magnitude of the transfer function dB is minus 20 log x. So here I have minus 20 log of x. And now let us consider a second point, point number 2 at 10, where omega over omega 0 is equal to 10x. It is 10 times the frequency at 0.1. So let us look at this point 2 here. And if omega over omega 0 is equal to 10x, this implies that the 20 log magnitude of t at this point is equal to minus 20 log of omega over omega 0, which is equal to minus 20 log of 10x. Okay? But minus 20 log of 10x is equal to minus 20 log x minus 20 log 10, which is equal to minus 20 log x minus 20 dBs. Therefore, when I moved from point 1 to point 2, okay, when the frequency was multiplied by 10, okay, the gain dropped by minus 20 dBs. Okay, the gain dropped by minus 20 dBs. Therefore, here this is how we derive the term minus 20 dBs per decade. يعني every 10x we're going to drop by 20 dBs. Hence, we represent the pole by a 0 dB gain before the 3 dB frequency or the cutoff frequency, and a line with a slope equal to minus 20 dBs per decade after we hit the cutoff frequency. Okay, great. And I will take rules how to handle multiple poles later. But first, let us now jump. So this is the summary of the slides. Let us now jump to the phase plot. How do we draw the phase plot? So again, given the same transfer function, we have a frequency omega 0, a pole at omega 0. We draw 2 points. The first point is 0.1 omega 0, and the second point is 10 times omega 0. Okay, and we use this to be able to draw the contribution or the phase Bode plot. Now, what is the angle of t? If we want to know what's the angle of t, it is the angle of the numerator minus the angle of the denominator. The angle of the numerator is 0, and the angle of the denominator is nothing but arctangent. The angle at the denominator is arctangent of b over a, which is omega over omega 0. Okay, so we are going to divide now the space into 3 regions. Okay, when omega is very small, so this is region 1 or region A. When omega is very small, smaller than 0.1 omega 0, we can safely assume that omega is small, okay, such that omega over omega 0 is approximately 0, okay, and this implies that I have arctangent of 0, and so the angle of t will be equal to 0, okay, and this is represented here by this line here. Now we will take another region, which is region B, let us take region C first. Region C, which is here beyond 10 omega 0. So in region C, omega is much greater than omega 0, and it is bigger than 10 omega 0. And in this case, the angle of t, which is equal to the minus arctangent of omega over omega 0, we will assume that it is equal to minus arctangent of a large number, say infinity asymptotically, and therefore it is going to be equal to minus 90 degrees. So we represent the contribution or the line asymptotically by minus 90 degrees. Okay, the phase is equal to minus 90 degrees. Then region B, we know its boundary points. Okay, we know we're gonna gain 90 degrees across it. This is 0.1 to omega 0, and this is 1 decade, and this is 2 decades. So basically, this region has minus 45 degrees, a slope of minus 45 degrees per decade, and at 2 decades, ربحت minus 90. Okay, but we also know that this also satisfies my requirement that at omega equal to omega 0, the angle of T equals to the minus arctangent of omega over omega 0, which is equal to minus arctangent of 1, اللي هي minus 45 degrees. فإذا we satisfy that at large omega I would have gained minus 90 degrees, and that's what the maximum phase I can reach in absolute value. At omega equal omega 0, I am at minus 45 degrees. For small omega, I have 0 degrees, and beyond it for large omega, I have minus 90 degrees. The remaining part of the lecture is going to handle things as follows. We have a circuit representation. We can find the transfer function from it. We would like, not all transfer functions are simple like the one we studied, but they will have poles and zeros. And once we determine these poles and zeros, we would like to estimate the 3 dB frequency either from the dominant pole or from an approximation or using the exact method. And we will cover this soon. For example, from the circuit which we studied before the first time, we found that the gain is of the form k over 1 plus s over omega 0. And in this example, this means that, so this still has one pole, that the magnitude of t, as we said before, that or the 20 log magnitude of t is equal to 20 log k minus 20 log the square root of 1 plus omega over omega 0 all squared. Okay, so now we have a constant term. And now we know how we draw the latter term, which was 0 dB until omega 0, and then it drops down with a slope minus 20 dB per decade afterwards. For my transfer function, what is going to happen is I'm going to add 20 log k to all of this curve. So we will wind up with a dB plot, which is 20 log k, that starts at 20 log k, which is the midband gain or the low frequency gain. And then we will have, once we hit omega 0, we will have a slope dropping at minus 20 dB per decade. Okay, we're going to learn rules how we handle that. So let us now navigate through these slides first to see what they are telling us. Okay, so as we said last time, this is a low pass single time constant. K is the low frequency gain, and omega 0 is the 3 dB frequency. So the transfer function is characterized by the low frequency gain and the 3 dB frequency. We also have other names for it, which are the corner frequency cutoff or the half power frequency. And the slope, we explained that the slope after omega 0 is minus 20 dB per decade, and a decade is a 10 times a change in in the frequency. As the frequency increases by 10x, the gain drops by 20 dBs. Okay, and we studied that at omega 0, we are at minus 3 dB frequency. And if we would like to look at the Bode plot, if we have the Bode plot for this circuit, we said that we will start at a 20 log K, and then at omega 0 we will have a 3 dB plot, and that we will have a slope here such that at 10 omega 0 we will have around 20K minus 20 dBs. Yani if I know that in the beginning the low frequency gain is 20 log K in dBs, and we start to drop at omega 0 here, then we know at 10 omega 0, okay, we are going to be at 20 log K minus 20, لأنه نحن we drop at a rate of minus 20 dBs per decade. Okay, now similar to the Bode plot magnitude, we have also a phase plot. Here they drew omega over omega 0, as we said that at 0.1 omega 0 will be at 0, at 10 omega 0 the asymptotic plot will be at minus 90 degrees, and at omega 0 the phase will be minus 45 degrees. Here the line in blue is really showing us the exact curve, and they are showing us that there is some error to the asymptotic phase Bode. Last time we covered how to calculate the response at the different frequencies, so I'm going to skip this. And we will put a little note here where we say we will not consider any parasitic effects at the low frequency. We only consider the effects that they pop up at high frequency. Okay, and basically we will be looking at the cutoff for the 3 dB frequency. This is what matters to us. Now, let us look at this function. Let us consider this function. This function represents the high frequency gain of a specific circuit. And here we see that this whole term when S tends to 0 is equal to AM. So AM represents really the low frequency gain component. And we have several zeros in the numerator and several poles in the denominator. And we have a specific set of requirements. The zeros are the zero frequency. They can be positive, negative, or infinite. لأن stability, I don't know why they can be infinite. Well, if they are infinite, this means that this term really goes away, it becomes 1, right? Because omega tending to infinity, it cancels that term. The poles, the WPs are the pole frequencies, and they are positive and real. هلا positive لأنه 1 plus S over, as a value, لأنه 1 plus S over omega P equals to 0 if and only if basically I have a pole at S equals to minus omega P, right? So it has to be in the left half plane, so we want these to be positive and real. Now, if I have that many poles, how do I determine what is the cutoff frequency of H for my amplifier? I need to approximate it. So there are 3 methods of approximation as we just discussed. The first method of approximation is the dominant pole. Okay, yeah. If I have the different poles WP1, and this is the axis of the frequency, followed by WP2, let us say, followed by WZ1. The smallest one, okay, I check on it, and I double check if omega P1 is much smaller than all other poles, and then the absolute value of the other zeros, then I can assume that this is the dominant pole. Okay, and I would approximate the 3 dB frequency to be approximately equal to this dominant pole. Now, there has to be a criteria on the ratio or the value, and we say it has to be 2 octaves down or less by a factor of 4. يعني for example إذا أنا عندي هون 1 megahertz هي omega P2 وإذا عندي magnitude of omega Z1 at 10 gigahertz, okay, and then I have a frequency at, let us say, 1 kilohertz, omega P1, then I can easily say this is the dominant pole because 1 kilohertz is definitely much less than, right, the 1 megahertz, right? And the ratio from this to this is more than 4 times. This is 1000x here. Okay, so if omega P1 is less by a factor of 4, يعني omega P1 على next smallest, okay, is less by a factor of 4 or more, then we are clear and we can declare this as the dominant pole. Okay, so then we can say that A of S is approximately equal to AM over 1 plus S over omega P1. We represented by a simple low-pass filter, okay, where omega P1 represents my 3 dB frequency, approximately. Okay, هيدي هي dominant pole approximation. Now we have another method, which is the better approximation. It is derived from the mathematical expression of the magnitude of a certain transfer function. And we can apply this method if one pole is obviously smaller than the other zeros and fours. يعني هون مش بالضرورة تكون 4 times smaller, ممكن تكون 2 times smaller. Okay, but it has to be obviously smaller, not very close. And we're not going to derive the mathematics, but we can use the equation. And the equation says that the 3 dB frequency can be approximated as 1 over the square root of the summation of 1 omega pi squared, okay, minus 2 times the summation of 1 over omega zi squared. Okay, and this has the 2, as you will see next, comes roughly from the exact estimation, and over root 2 is 3 dB frequency, but here we're just going to use the equation as this. And if in the midterm you use the better approximation or use them, then you use it. If we tell you use the most suitable, if you find it is larger by a factor of 4, you use dominant pole. If you find that it is obviously, pardon me, smaller, if you find that it is obviously smaller but not by a factor of 4, you will use the better approximation method. Okay, hello. The third method is the exact solution. يعني in order to find the 3 dB frequency, we know that the magnitude of T at 3 dB is equal to the low frequency gain over root 2. Okay, طيب نحن بحالة ال A of S, we know that the A of S has a low frequency gain which is equal to AM. يعني A of S, magnitude of A at omega 3 dB is really equal to AM over root 2. بس نحن we know that the magnitude of A at any frequency, how to calculate it. So we set it to be equal to AM over root 2 and we perform our calculations. Okay, so here we know, for example, if A of S is equal to AM ضرب product of 1 plus S over omega Zi over the product of 1 plus S over omega Pi. Okay, then the magnitude of A is equal to طبعا absolute value of AM times the product of the square root of 1 plus omega over omega zi squared over the product of the square root of 1 plus omega over omega pi all squared. Okay, and who we are seeing here in this expanded expression, and we want this to be magnitude of am over root 2, so we cancel am from both sides and we end up with this relationship here. Okay, so once we have this relationship here, what we are going to say is we are going to square both sides, and when we square both sides we end up with this equation. So when we square both sides, we get rid of the square roots. So, and then we will cross multiply, and we're going to set x equals omega squared h. يعني أول شيء حنبلش نقول إنه 1 plus omega over omega z1 all squared into 1 plus omega over omega z2 all squared. Okay. This is going to be equal multiplied by 2 and in square root to cross multiply. This is going to be equal to 1 plus omega over omega p1 squared into 1 plus omega over omega p2 squared dot dot. Okay, and we want now to substitute in this expression omega equal omega 3 dB to solve for it. So this will be omega h, and omega h which we are solving for. Okay, now what we do is we substitute for omega h squared x, and we end up with this expression here. So we end up with an expression where we will have, let us remove this here. Okay, so we'll end up if we remove this here. For the z's, we will have here 1 plus x over omega z1 squared into 1 plus x over omega z2 squared, and the same for the poles. We will end up with 1 plus x over omega p1 squared into 1 plus x over omega p2 squared. طبعا if I have more terms I have to continue multiplying. We solve for x and then we take the square root in order to obtain the 3 dB frequency. هلا أنتم for your sake, if you have the a of s already in reduced form, which is an into 1 plus s over omega zi, okay, over the product of 1 plus s over omega pi, then you can automatically use this equation, okay, with the pi's and the omega zi's, okay, solve for x. حسب قد ايه عندنا terms هون, we will have terms here and the same will have terms here. You solve for x and then you take the square root in order to find the 3 dB frequency. Okay. هلا here we will take an example. So I have A of S here. The low frequency gain AM is equal to 1. Okay, so I don't have to worry about it. And I have the remaining terms where I have, let us look at this. In the numerator, I have omega z1 equal minus 10 to the 5. Careful about the sign. In the denominator, I have omega p1 equal 10 to the 4. And I have omega p2 equal 4 times 10 to the 4. Okay, and here they are going to tell me that I have 2 zeros. ليش؟ لأن I have 2 terms in the denominator. I really have 2 terms in the numerator, but this is 1 plus s over infinity. Hello, we don't have to worry about this, okay? What we really care for is to sort these poles and zeros in absolute value. يعني أنا إذا جيت حطيت scale, the smallest is 10 to the 4, P1, and then the second smallest is 4 times 10 to the 4. Here it's pole 2, and then the third smallest in absolute value here 10 to the 5 اللي هي the first zero. If we look at this, the smallest pole is at least 4x smaller than the next one. Therefore, if I want to, I can use the dominant pole, and I can say, according to the dominant pole, my omega h is approximately 10 to the 4 radians per second, or my omega 3 dB is around 10 to the 4 radians per second. Hello. So for the dominant pole, we set it 10 to the 4. For the better approximation, we're going to apply the formula, plug in the numbers, طبعا هي 0, don't worry about it. So we get 9,800 radians per second. For the exact solution, we're going literally to write the equation, لأن هي product of 1 plus x على omega pi equals to 2 direct product of 1 plus x على omega zi. The nice thing here is that we have two poles, so we'll end up with a quadratic equation. يعني x هتكون of order 2. And if we expand this mathematical term, we will wind up with a 3 dB frequency around 9.573 radians per second. So you can see how the approximation, for example, for the 3 dB frequency is around 5% far from the dominant pole, from the exact solution. And the better approximation is indeed better because we are closer to the exact solution. Okay.